Hi, we'll now be determining the polarity of molecules using a few examples. Before we can determine whether or not a molecule is polar, a number of things about a molecule must be known. One, whether or not the bonds within the molecule are polar. Number two, the number of bonds within the molecule. And finally, the geometry of the molecule. To know whether or not a bond is polar, we need to know there is a difference of electronegativity of more than 0.4 between the two bonded atoms. This table here shows the electronegativity values that are ascribed to these different elements here. We will now use the models of a few molecules to illustrate how their polarities can be determined. We start first with the diatomic molecules. As the name indicates, a diatomic molecule is made up of only two atoms. There are two types of diatomic molecules, those that are homonuclear and those that are heteronuclear. These two here are examples of homonuclear molecules. This one here is the chlorine molecule, and this one here is the hydrogen molecule. As you can see, the atoms within these molecules are identical. And because of that, there's no difference in electronegativity between these two bonded atoms. The bond here will be nonpolar, and the molecule also be nonpolar. The same can be said of this one and all other diatomic homonuclear molecules. These ones here are examples of heteronuclear molecules. This one here is hydrogen chloride, this is hydrogen bromide, and this is hydrogen iodide. In this molecule here, the chlorine is more electronegative than the hydrogen, and the difference in electronegativity between these two atoms is 0.9. And because of that, the bond here becomes polar. In this case, the electron cloud will shift towards the chlorine side here, and that will acquire small negative charge, and the hydrogen there acquires small positive charge. We say that the bond is polar, and the molecule is also polar. This is hydrogen bromide. The same thing can be said about this, but the only thing is that the difference in electronegativity between these two is 0.7. This one is more polar than this one because of a greater electron shift than in this case. One thing I wanted to bring to your attention is that in the book on page 63, I mistakenly put the value for chlorine as 3.5. It should be 3. Okay, so the electronegativity value for chlorine is 3 and not 3.5. This one here is hydrogen iodide. It is also heteronuclear, but the difference in electronegativity between these two atoms here is only 0.4, and it is therefore considered to be a non-polar molecule. So generally speaking, all homonuclear diatomic molecules are non-polar. Heteronuclear diatomic molecules can be either polar or non-polar. They're polar if the difference in electronegativity between the two bonded atoms is greater than 0.4. If not, like in this case, they're all non-polar. In today's lesson, we'll try to learn how to determine whether or not a simple polyatomic molecule is polar. A simple polyatomic molecule, as can be recalled, has a central atom surrounded by other atoms that we call the peripheral atoms. This molecule here, which is methane, has carbon as its central atom and 4 hydrogen atoms as the peripheral atoms. A polyatomic molecule can become polar in one of two ways. The first way that it can become polar is when there is a net shift of electron cloud away from the central atom towards the peripheral atoms. In such a case, the central atom will acquire a small positive charge, and each of the peripheral atoms will acquire a small negative charge. Or, in the second case, what will happen is this. There can be a shift of the electron cloud away from these peripheral atoms towards the central atom. In such a case, the central atom would acquire a small negative charge, and each of the peripheral atoms will acquire a small positive charge. So what we'll do now, we'll start by trying to determine the polarities of a few AX4 type of molecules. The first one that we're starting with is this methane molecule here. So what we have done to enable us to determine whether or not these molecules are polar is devising a few strategies. And these are simple questions that we answer. Number one, we ask whether or not the bond within the molecule are polar. In this case, the bond here is nonpolar. The CH bond has a difference of electronegativity of only 0.4. As such, we'll say that each of these bonds here is nonpolar. And when that happens, if all the bonds within a molecule are nonpolar, then the molecule as a whole will be nonpolar. The other AX4 type of molecule that you study is carbon tetrafluoride. Recall that AX4 type of molecules have a central atom that is surrounded by 4 peripheral atoms. Each of these bonds here make an angle of 109.5 degrees, and the molecule has a geometry of a tetrahedron. So we'll go through the strategies now to determine whether or not this molecule is polar. So the first question that is asked is, are the bonds polar here? Yes. The difference in electronegativity between carbon and fluorine is 1.5. And therefore we say that each of these bonds here is polar. The next question that is asked is, which of the two bonded atoms is more electronegative? In this case, the fluorine atom is more electronegative than the carbon atom. Why we need to know that? We need to know that because we will say that the atom that is more electronegative will be putting electrons away from the other one to which it is bonded. In this case, each of the fluorine atom will be pulling electron cloud away from the central carbon atom. We can also say that each of the fluorine atoms is exerting a pulling force on the central carbon atom. The third thing we have to determine is this. In which direction would the resultant force on the central atom be? Okay? Now, in this case, we try to find the direction of the resultant force on the central carbon. Now we are having 4 equal pulling forces separated at equal angles away from each other. The conclusion that can be made will be that there will be no resultant force on the central carbon atom. That means when there is no resultant force on the central carbon atom, there will be no net shift of electron either way from the central atom to the peripheral atoms, or from the peripheral atoms to the central atom. As such, the molecule will be nonpolar, even though the bonds are polar. Let us say we had a different molecule now, in which the central atom was more electronegative than the peripheral atoms. In such a case now, the central atom will be pulling electron cloud away from the 4 peripheral atoms. Or we can say that each of the peripheral atoms is pushing onto the central atom with the same force. Again, if we try to find the resultant force on the central atom, because there are 4 equal pushing forces separated by the same angle, we say that the resultant force on this central atom will be 0. There will be no net shift of electron cloud in either direction, and the molecule will be nonpolar. So we can make a blanket statement that all AX4 type of molecules are nonpolar. However, we can come back to this methane molecule here. You want to give a different perspective now. Suppose that we removed one of these and replaced it by a chlorine atom now. If we did that, we'll be distorting the forces within the molecule. In this case, push, push, pull. This chlorine atom, because much more electronegative than these hydrogen atoms here, will be pulling electrons in this direction. As such, it will acquire a small negative charge, and each of these hydrogen here would acquire a small positive charge. If you replace another hydrogen by another chlorine atom, the effect will be even more profound. You have greater shift of the electron cloud in this direction. You have bigger negative charges here and bigger positive charges here, and the molecule will become even more polar. We should now try to determine the polarities of a few AX3 E-type of molecules. Recall that in these molecules there is a central atom that is surrounded by 3 peripheral atoms and a lone pair of electrons. Each of these bonds here is separated from each other by an angle of 107 degrees, and the molecules have a trigonal pyramidal geometry. So the first molecule that we'll be examining is this pH3 molecule. So what we'll do here to determine its polarity is going through the strategies that we have developed. We try to answer the first question: are the bonds polar within the molecule? The answer to that is no, because the difference between phosphorus and hydrogen in electronegativity is only 0.01. As such, all the bonds within this molecule will be nonpolar, and as such, the entire molecule will be nonpolar, so we mercilessly dispose of this molecule. I'm a merciful person, sorry. The other molecule is the ammonia molecule. Again, it has the same characteristics as any A3 E-type of molecule. Only in this case now you have a central nitrogen atom that is surrounded by 3 peripheral hydrogen atoms and this lone pair of electrons here. So let's go through the strategies, answer the questions. Are the bonds polar? Yes, the bonds are polar because the difference in electronegativity between hydrogen and nitrogen is 0.9. Next, which of these 2 bonded atoms here is more electronegative? The nitrogen atom is more electronegative than the hydrogen atom. As such, the nitrogen atom will be pulling on the hydrogen atoms with a greater force. That is, it will try to pull electron clouds away from the hydrogen atoms. Or we can simply say that each of those hydrogen there is pushing onto the nitrogen atom with a certain force. So the next thing is, how do we find the direction of the resultant force on the central nitrogen atom? This necessitates a bit of spatial thinking. Now, here we are having 3 forces from the bottom. Remember, this thing has a trigonal pyramidal geometry. So we have 3 of these atoms which are below this nitrogen here, pushing onto the nitrogen. So which direction you think the central atom will move? If you said it will move in this direction, then you're right. The resultant force on this nitrogen atom here will be in this direction. All that means is this. It means that there's a net shift of the electron cloud away from the peripheral hydrogen atoms towards the nitrogen atom. What is the result? The result is that this nitrogen atom here acquiring a small negative charge, and each of these hydrogen atoms here acquiring a small positive charge. As such, the ammonia molecule is polar. The other molecule that we are looking at is phosphorus trichloride. Here we are having a central phosphorus atom surrounded by 3 peripheral chlorine atoms and a lone pair of electrons. So we go through the strategies again. What do we ask? Are the bonds polar? Yes. There is a difference of electronegativity between this phosphorus and the chlorine atom of 0.9. As such, each of these bonds here is polar. Which of the two bonded atoms is more electronegative? The chlorine atoms are more electronegative than the phosphorus atom. As such, the chlorine atoms will be pulling electron cloud away from the phosphorus atoms. Or we can say that each chlorine atom is exerting a pulling force on the central phosphorus atom downwards. In which direction will the resultant force on the phosphorus atom be? You have to do some spatial thinking there. Beneath that phosphorus atom there, you have 3 guys are pulling down on it. So the obvious answer to that will be in this direction. It will be going downwards. Okay, so the resultant force at that side is downward, means that there will be a net shift of the electron cloud away from the phosphorus atom towards each of the chlorine atoms. As such, each of the chlorine atoms will acquire a small negative charge, and this phosphorus atom here will acquire a small positive charge, and that will make the molecule become polar. We will now try to determine the polarities of a few AX2E type of molecules. Recall that such type of molecules have a central atom that is surrounded by 2 peripheral atoms and 2 lone pair of electrons. The bond angle that these atoms make, the peripheral atoms make with each other, is 105 degrees, and its molecular geometry is said to be V-shaped or bent. The molecule that we first be studying is the water molecule. So we'll go through the strategies, okay? We'll ask whether or not this bond here is polar. Of course, we know this is H2O. This is oxygen and that is hydrogen. We'll ask the question, is this bond polar? Yes, the bond is polar, and because the difference in electronegativity between hydrogen and oxygen is 1.4. Both of these bonds are polar. Which atom is more electronegative? The oxygen atom is more electronegative than the hydrogen atom. As such, the oxygen atom, being more electronegative, will be pulling electron cloud away from both of these hydrogen atoms. Or we can simply say that the hydrogen atoms are pushing onto the oxygen atom with a force. So, point number 3, in which direction will the resultant force on this central oxygen atom be? So here again, it won't be difficult to determine that. Here you have 2 forces from the bottom pushing onto the central oxygen atom, and therefore what do you think? In which direction do you think that this oxygen atom move? The obvious answer should be upwards like that. That means that there is a net shift of electron cloud away from the hydrogen atoms towards the oxygen atom. The result is the oxygen atom acquiring a small negative charge, and each of these hydrogen acquiring a small positive charge, making the water molecule polar. If we had hydrogen sulfide, let us say instead of oxygen that was sulfur, All the characteristics of the molecules remain the same. And we can ask the question now, would hydrogen sulfide be a polar molecule or not? The bond there will be non-polar, okay, because the difference between sulfur and hydrogen is only 0.4, and therefore a molecule will be non-polar. The other type of molecules you want to study today is AX3 type of molecules. Here we are having boron trihydride. In these molecules, there's a central atom that is surrounded by 3 peripheral atoms that are separated by a bond angle each of 120 degrees. And the geometry of this molecule is said to be trigonal, planar, flat molecule. Okay, now we try to figure out whether boron trihydride is polar or not. First question is the bond polar? Yes, the bond is polar because the difference in electronegativity between boron and hydrogen is 0.6. Which of the two bonds here is more electronegative? The boron atom is more electronegative than the hydrogen atom there. Therefore, the boron atom will be pulling electron cloud away from the hydrogen atoms. Or we can simply say that each of the hydrogen is exerting a pushing force on the boron atom there. Finally, in which direction would the resultant force be on the central boron atom? Here we are having now 3 equal forces pushing on this boron atom, separated by 120 degrees. What do you think? Would there be a resultant force on the boron atom? The forces will cancel out, and therefore there will be no resultant force on the boron atom. As such, this molecule will be nonpolar. We can try another one out. You can try boron trichloride. Same characteristics as that. You go through the strategies. Are the bonds polar? Yes. There's a difference in electronegativity between boron and chlorine of 1.2. The chlorine is more electronegative. Therefore, each chlorine atom will be pulling electron cloud away from the boron atom. Finally, what will be the resultant force on the boron atom? Now we are having 3 equal forces separated by the same angle of 120 degrees, pulling on this central boron atom here. The result will be there will be no resultant force on this boron atom here. There will be no shift of electron in either direction, either from this one to these ones here or these one to that one, and therefore this molecule will be nonpolar. The final type of molecules we're going to talk about is AX2 type of molecule. An example of that is carbon dioxide. You can see in these type of molecules, there's a central atom here that's surrounded by 2 peripheral atoms at 180 degrees away from each other. And the molecule is linear. Now let's go through the strategies. Ask the question, are these bonds here polar? The answer is yes, because there's a difference in electronegativity of 1 between oxygen and carbon. Which is more electronegative? The oxygen is more electronegative. So there will be a pulling force in this direction and a pulling force in this direction. Finally, in which direction would the resultant force be on the central carbon atom? Since both of these are pulling in opposite direction with the same force at 180 degrees, there will be no resultant force on the central carbon there, and therefore the molecule will be nonpolar. That is why carbon dioxide will be nonpolar. All AXE2 type of molecules will be nonpolar. I hope that these little demonstrations using these models and so on was able to make you get a better understanding how to decide whether or not these simple molecules are polar. Well, thank you for listening.